All right, so we've talked a lot about critical points and extreme values, mins and maxes, things like that. So now we're ready to talk about increasing and decreasing functions and the first derivative, f prime of x. So when we talk about increasing and decreasing functions, what we want to look at is, look at the graph of the function f of x and see what happens when x increases. So remember, the positive direction for x is to the right. So, positive to the right, negative to the left. So when x increases, that's when x moves to the right. So you want to look at the graph, see what happens when x moves to the right. And if y increases, meaning if the y coordinates go up, then we say f of x is increasing. And if the y coordinates are decreasing, meaning the y coordinates are moving down on the graph, then we say f of x is decreasing. So it's pretty straightforward. You also might remember this from your pre-calculus or college algebra courses. But anyway, let's see a brief example with this. So we'll put a graph over here. X-axis, y-axis. Let's zoom out just a bit. So let's say we have a function that does something kind of sort of like this. So here is y equals f of x. Right? And let's put 4 right here. So this will be the point where x equals 4, and then this could be the point where x equals 1, just for example. So notice, let's examine this graph in terms of increasing and decreasing. So remember, we have to look what happens when x increases, so moves left to right. So basically we're going to look what's happening with this function, with this graph, as x moves to the right. Well, if we come in here from the left to the right, then we see that the y-coordinates are going up, right? Here the y-coordinates, they're increasing. So we don't know exactly what they are, but we don't really care. All we care about is that they're increasing, they're getting larger. So as x increases, y is also increasing, and that means that f of x is increasing on this interval here from negative infinity all the way up to x equals 1. So on negative infinity up to 1. Okay. So it's negative infinity to 1 because here this function is increasing the entire time it comes in from x equals negative, or from negative infinity. So x comes in from all the way over here, and it's the whole time x is coming in, it's increasing that entire time up until you get to x equals 1. Then the function turns around and starts decreasing. Okay. So let's use shorthand notation now for increasing and decreasing. So increasing is going to be this up arrow like this, and then decreasing, so f of x is decreasing, which will be this shorthand notation here, arrow pointing downward. So f of x is decreasing on which interval? Well, here it starts decreasing when x equals 1, and then it decreases the whole time until you get to x equals 4, because then the function starts increasing again. The y-coordinates start getting larger. But here between 1 and 4, the y-coordinates are getting smaller the whole time. So the function is decreasing on the interval from 1 to 4. So when you talk about where a function is increasing and decreasing, you always want to use the x values. Okay, you don't want to talk about the y values when you describe the intervals. So here, this is decreasing on the interval x equals 1 to x equals 4. And then one more, so f of x is increasing. F of x is increasing. Again, this shorthand notation, which we'll just use this from now on, the shorthand notation, on 4 all the way over to infinity. So here, when x is larger than 4, the function is just increasing the whole time. It never turns back around. It's just shooting up, up, up this way, never stopping. So increasing on 4 to positive infinity. Okay, so notice we're using open intervals to describe these. Some people, they prefer to use closed intervals where they'll include the endpoint 1, or they'll include 1 and 4 here, or they'll include 4 here. But very technically speaking, the function isn't actually increasing at 1, and it's not actually increasing or decreasing at 1 or 4, basically. So it's a little strange to include the endpoints, I think so anyway. But depending on who you talk to, that's it's just a personal preference, I guess. Some textbooks I see, they do it like this. Some textbooks, they include the endpoints. It really just depends on your textbook or your instructor or things like that. Okay, but for now, so let's see, how does this all relate to derivatives? So here we're talking about increasing, decreasing functions and the first derivative, f prime of x. So what does this have to do with derivatives? Well, remember, we said that the derivative is slope, right? So we've said that in a few videos, in a few earlier videos. So the derivative is the exact same thing as slope. Okay, so f prime of x, that gives you the slope of the function, or in other words, the slope of the tangent line at a point, et cetera, et cetera. But basically, derivative is slope. So that's one of the key points we want to remember about derivatives. So, and what does slope tell us? Slope tells us if a function is increasing or decreasing. So basically, just think of it in terms of straight lines. If you have a straight line that's increasing, it has a positive slope, right? A straight line that's decreasing, that's a negative slope. Well, the same exact principle applies to functions in general, functions like this, any kind of function you could think of, really. If the function is increasing, then that means the slope at each point where it's increasing is going to be positive. In other words, the derivative is positive. Okay, so basically a positive derivative means an increasing function. Okay, because, and the reason is that derivative is slope. And if the function is increasing, then you're just going to have a positive derivative. So think about, what if we put a tangent line, let's draw a tangent line right here. So we know the function is increasing here, right? It's increasing on the interval negative infinity to 1. So let's draw a tangent line here. So if we try to draw a tangent line, notice, so here this line is tangent right here. So the derivative of the function at this point, whatever it may be, maybe negative 1/4, for example, the derivative is going to be positive, right? Because the tangent line has a positive slope, right? So here's our tangent line here with a positive slope. And likewise, if we draw a tangent line over here, say, I don't know, at x equals 2-ish, this is going to have a negative slope, right? This tangent line has a negative slope. And because that tangent line is going down, so it has a negative slope. And we know the function is decreasing on this interval from 1 to 4. So the derivative for all x between x equals 1 and x equals 4 is going to be a negative derivative. And we see that here. Here's a negative slope of the tangent line, right? So, and remember, slope of the tangent line is the same thing as the derivative. And likewise over here, if this is, say, x equals 6, for example, the tangent line here is going to be, or it's going to have a positive slope. Okay. So here, increasing function on this interval, the function is increasing on this interval, and the tangent line has a positive slope, so the derivative is going to be positive here, right? So basically, the point we want to make here is, so let's summarize the point we just made. Increasing, let's separate this. Increasing function is the exact same thing as positive slope. All right. And remember, increasing function, that means f of x is increasing, right? So the y values are going up. And then positive slope means f prime of x is greater than 0, right? So f of x is increasing means f prime of x is greater than 0. And likewise, decreasing function is the exact same thing as negative slope. And remember, decreasing function, that's just in shorthand notation, that's f of x, down arrow like this. F of x is decreasing. And then negative slope. So remember, slope is f prime of x and negative less than 0. So this is what we have going on here. Let's separate these just for readability, I guess. So here, if we have an increasing function, so if f of x is increasing, then that's the exact same thing as saying f prime of x is positive. If we have a function that's decreasing, so f of x is decreasing, then that's the exact same thing as saying f prime of x is less than 0, right? So that's sort of the major point here, and it lays the foundation for what's called the first derivative test, which we'll talk about in a later video, maybe the next video. So let's think about this. we'll apply this to the picture we just drew over here. So we know this function, let's zoom out just a bit, this function is increasing on negative infinity to 1, it's decreasing on 1 to 4, and it's increasing again on 4 to infinity. So if we apply what we did over here, or what we said over here, to that, then we can say, okay, in that case, f prime of x, for this picture up here, f prime of x is greater than 0 on negative infinity to 1, f prime of x is less than 0 on 1 to 4, okay, and f prime of x is greater than 0 again on 4 to positive infinity. Okay, so here f of x is increasing on negative infinity to 1, which means f prime of x is positive on negative infinity to 1, because remember, f of x increasing is the same thing as saying f prime of x is positive, right? That's what we said over here. And f of x decreasing is the exact same thing as f prime of x is negative. So here, since f of x is decreasing on 1 to 4, then f prime of x is negative, less than 0 on 1 to 4. And then again, since f of x is increasing on 4 to infinity, then f prime of x is greater than 0 on 4 to infinity, right? So that's just sort of an introduction to this. So let's see a quick example using an actual function, that we have that's actually algebraically defined and not just like a general picture here. So let's make some room here. So we'll do an example of how to figure out, just if we just have a function with no graph to look at, we'll do an example of how to figure this stuff out. And we're going to want to use this here, so maybe I'll leave this here, because we're going to want to refer back to it. Okay, so let's say we have example 1. Let's say, for example, we want to find the intervals where f of x is increasing and where f of x is decreasing. Okay, so we're going to be given a function f of x, and let's zoom in just a bit, and we want to find the intervals where the function is increasing and where it is decreasing. So let's say our function that we're given is f of x equals x squared minus 4x. So not a very complicated function, right? We probably already know what that looks like, but it's best to start off with simple examples that we already know much about so that we can see just how this stuff kind of works. So, all right, we want to find the intervals where f of x is increasing and where it's decreasing. So here's our f of x. So what we have to do is analyze the derivative, okay? So, we just by looking at this algebraically, we can't automatically say, oh, okay, it's increasing, decreasing on certain intervals here. But what we can do is take the derivative, and then we can find out when the derivative is positive and where the derivative is negative. And then we could analyze it just in terms of this. So we know once we find the intervals where the derivative is positive, then we know that's where the function is increasing. And likewise, once we find the intervals where the derivative is negative, then we know that those are the intervals where the original function is decreasing. So here, if this is f of x, then f prime of x is just going to be 2x minus 4, right? So 2x minus 4. All right. Now what we do is we set this equal to 0. So set it equal to 0. Okay, so now 2x minus 4 equals 0. We want to solve that for x. So basically just add 4 to both sides. 2x equals 4. Divide both sides by 2. We get x equals 2. Okay? So now here, this the derivative is 0 here. So actually remember, this is going to be a critical point, right? But we're not really thinking of this in terms of critical points yet. That'll come in the later video, maybe the next video. So here, the derivative is 0 when x equals 2. So what we do now is set up what's called a sign chart. So we're going to set up a sign, S-I-G-N, sign chart. So now what that is just going to be a little chart like this. So you always want to label your sign chart. So this is a sign chart for f prime, for the derivative f prime. Now what we can do is put 2. Okay, the derivative is 0 when x is 2. So we'll put 2 here. All right, now what do we have here? We have all the numbers greater than 2 are over here. All the numbers less than 2 are over here. Now what we have to do is pick just one number, any number in each of these intervals. Okay, just pick one number, any number at all that we want in each of these intervals, and then evaluate the derivative at that point. So 0 is in this interval, right? Because 0 is less than 2, so 0 is over here. So let's do that. Let's say f prime of 0. Now what does that equal? Well, let's go back over here. F prime of x is 2x minus 4, so f prime of 0 is 2 times 0 minus 4, which is 0 minus 4, which is negative 4, which is less than 0. Okay? So f primed of 0 is negative. So that means the derivative is negative in this entire interval, right? So if you're wondering, why is it okay to just pick one point and do that? Well, we know the only place where the derivative is 0 is x equals 2. So if you're to the left of 2, then the derivative has to be the same sign all the time, always. Because, if the derivative changes from negative to positive somewhere in here, then that means it has to cross 0 again, because, this is continuous, right? This derivative, it's 2x minus 4 is a continuous function. So if it ever becomes positive, if the derivative ever becomes positive in here, then it has to cross 0 again. But we know the only place where it crosses 0 is here when x equals 2. Okay, so basically what that means is, since x equals 2 is the only place where the derivative is 0, then to the left of x equals 2, the derivative has to have the same sign, always. To the right of x equals 2, the derivative has to have the same sign, always, right? So here, so let's see what happens. So now we have to pick one number in this interval, right? So let's say 3. 3 is larger than 2, so 3 is going to be over here, so that's a good one to pick. So f primed of 3 equals 2 times 3 minus 4, which is 6 minus 4, which is 2, which is positive. Okay? So that means that the derivative is positive in this entire interval. Okay? So here, what we just found out, and again, it's for the same reason, we only picked one number in here, but that's okay, because we know that the derivative is continuous, okay, in this whole interval, and the only place where the derivative is 0 is at x equals 2. So the only place where the derivative could possibly change sign is at x equals 2. Okay, so over here, since the derivative never crosses 0 again when x is larger than 2, then the derivative is stuck being only positive or only negative, right? So basically that's what's happening there. The derivative is not allowed to change sign again because it can only do that when it crosses 0, which is right here at x equals 2. So this is the only place that the derivative might change sign. And another point to make is it doesn't have to change sign. We'll see a few examples where something like that happens. But anyway, for now, we'll just stick with this. So here, what do we just find out? Well, we found out the derivative is negative on this interval here. And what's this interval? This is, well, let's write down what we found. So we just found out that f primed of x is less than 0 on this interval from negative infinity to 2. And we also just found out that f prime of x is greater than 0 on this interval from 2 to infinity. Okay. So what that means for us, okay, remember the original question was find the intervals where f of x is increasing and where f of x is decreasing. So here we just found out, just using algebra, no graphs or anything like that, just using analytic techniques here, we just found out where the derivative is negative and where it's positive. So now we can use this down here to say, okay, the derivative is negative on negative infinity to 2, so that means the function is decreasing on that interval. And here the derivative is positive on 2 to infinity, so that means the function, the original function, is increasing on that interval. So here, f of x is decreasing on negative infinity to 2 because the derivative is negative there. And let's zoom in a bit. And f of x is increasing on 2 to positive infinity because the derivative is positive there. Okay? So that's pretty much the answer for the question. That's how we do this. So again, just to recap real quick, let's zoom back out. So we'll just summarize what we did again. So we want to know where, find the intervals where f of x, this function f of x, is increasing and where it's decreasing. So what we do is we're given our f of x, x squared minus 4x. Now we can't just look at this and say, oh, okay, this function is this, so automatically I can say it's increasing, decreasing here, here. We can't do that. But what we have to do is take the derivative, find where the derivative is 0, because that's where the derivative is allowed to change signs, right? And then here, once we found that out, Also, in general, I just want to point out, you have to find where the derivative is 0 or where it's undefined, right? So basically, you're looking for critical points. But we'll talk more about that in the next video, I think. So here we found out where the derivative is 0, and then we set up the sign chart, SIGN sign chart for f prime. So always label your sign chart, put x equals 2 on the sign chart because that's where the derivative is 0. And then what we have to do is test the derivative in each of these intervals here. Okay, however many intervals you have, you just have to test the derivative in each one of those intervals. Here we only have 2, negative infinity 2, and then 2 to positive infinity. So then just pick one number from each interval, and then that's enough to test it in that interval. So then, we picked 0 in here. Okay, we picked x equals 0 in this interval, and then x equals 3 in this interval. And again, remember, so we said it a bunch of times, but it's worth saying again. The only place where the derivative might change sign is at x equals 2, because that's where the derivative is 0. But to the right of x equals 2, the derivative never touches 0, so it's stuck on one side of 0. And in this case, we just found out it's stuck on the positive side of 0. And then here, to the left of x equals 2, the derivative is never 0, so the derivative is stuck on the same side of 0. And in this case, it's stuck on the negative side of 0. Okay, so f prime of 0 is negative, f prime of 3 is positive, so that's how we got these here. And then we just use this here to say, okay, well, first of all, we said, all right, f prime of x is less than 0 on negative infinity to 2. That's what we found out here. And f prime of x is greater than 0 on 2 to infinity. That's what we found out here. So then we use this to say, all right, since the derivative is negative on that interval, then f of x is decreasing on that interval. And since the derivative is positive on that other interval, then the function is increasing on that other interval. So that pretty much wraps up this example. Let's just see a graphical not really interpretation, but let's just see what happens graphically with this. So x squared minus 4x, if we want to graph that, what's that going to look like? Well, let's see. That's just a parabola that opens upwards, and where are the x-intercepts? When x is 0, this guy is 0, and also when x is 2, or rather when x is 4, when x is 4, this guy is also 0. So we have x-intercepts, so let's draw f of x here. So x-axis, y-axis, so it's just going to be a parabola, right? So if you want to draw that, parabola, pretty bad picture, but it's just a parabola. So here is 4, here's 0, and then here's 2, right? So notice this function, this is y equals f of x. So here y equals f of x, let's zoom in a bit, it's decreasing on negative infinity to 2, just like we found, right? Just like we found. And f of x is increasing on 2 to infinity, just like we found here, right? So let's draw the derivative. So here's f of x, let's draw the derivative f prime of x. So f prime of x is just a straight line, right? 2x minus 4. Here's our derivative, 2x minus 4. So let's draw that. So, okay, x-axis, y-axis. I guess maybe we should move that over just a bit. So, y-axis. So 2x minus 4 is just a straight line, and basically it's a straight line with slope 2, and it's going to be down, push down 4. So it's kind of sort of something like that. Really not to scale, but eh. So 2x minus 4, this is the point where x equals 2, right? X equals 2 right here. And then this is negative 4 down here. So not really to scale. Anyway, this is y equals f prime of x. All right, and what do we see? We see here the derivative is negative when x is less than 2. So on negative infinity to 2, the derivative is negative, and on 2 to infinity, the derivative is positive. Okay, so it's important to not get confused between, increasing, decreasing function and positive, negative derivative. So here, yeah, the derivative is increasing, right? The derivative is increasing the whole time, but that doesn't matter. Okay, all we want to look at is where's the derivative negative and where's the derivative positive? Because negative derivative means decreasing function. Okay, negative derivative means decreasing function. And positive derivative means increasing function. Okay, so positive derivative, increasing function, negative derivative, decreasing function. So it doesn't matter where the derivative increases or decreases. It only matters where the derivative is negative or positive. And it doesn't matter where the function is positive or negative. It only matters where the function is decreasing or increasing. Okay, so that's kind of an important thing to keep straight is, it's increasing, decreasing function, but positive, negative derivative. So those are the things we want to look at. Those are the things we're concerned about here. So again, this whole thing lays the foundation for what's called the first derivative test, which is what you want to use, or one of the tools you could use to find local mins and local maxes once you have, once you find the critical points, things like that. And we'll start talking about that in the next video.